Good morning, everyone. Let's start today's workshop. I'm Shuta Nakajima from Kyoto University. I'm the chair of this session. We're happy to have Monika Schleier-Smith from Stanford University today. She will tell us about programmable interaction and emergent geometry with atoms and photons. Okay, please start, Monika.
Thank you so much for the invitation to participate in this conference. The title of my talk is Programmable Interactions and Emergent Geometry with Atoms and Photons. And as you can tell perhaps from the title, I am an experimental atomic physicist, which is perhaps a somewhat different background from many of you in the audience. But I thought I would start by kind of establishing some common ground by sharing a quote from actually an ancient philosopher. So this is Democritus, the inventor of the concept of the atom. And I recently found this wonderful quotation where he says, sweet and bitter, hot and cold color, all of these things are, he says, by convention. And in truth, there are but atoms and the void. So what does he mean by that? In modern language, you might say that what he's getting at is what at the time was a revolutionary concept, that things like taste and temperature and color, these macroscopic behaviors, really emerge at a more fundamental level from the microscopic configurations of individual atoms. So, these days, of course, that's well understood. One can even see individual atoms under a microscope. But he mentions atoms. He says, in truth, there are but atoms and the void. And I think what perhaps is a topic of interest to some of you in the audience is, do we really fully understand the void, right? So sort of a modern frontier for not only philosophers, but also physicists, is asking the question, what about space-time? Is space-time really smooth, or is there here also underlying some more fundamental microscopic description? Do curved space and gravity emerge also from some discrete constituents, like the atoms that are the foundation of taste and color and temperature? So here in this nice picture by Escher, the constituents are fish. We don't think in our universe the discrete constituents are fish. But I was certainly fascinated to learn about sort of the elegant concept of holographic duality, under which curved space and gravity might emerge fundamentally from entanglement among quantum mechanical degrees of freedom. And that's sort of illustrated here by this system on the boundary, perhaps being some system of qubits in blue, and the white lines indicating something about the structure of entanglement amongst them that manifests in some emergent bulk geometry. So, that's a fascinating concept, I think, both for asking about gravity in our universe and also asking, is this a useful tool for understanding and visualizing the properties of quantum many-body systems that might also have useful applications. And so, I was fascinated to learn about this idea and started to ask myself, what can one do if one wants to actually explore this in experiments? And broadly speaking, there are kind of a couple of different approaches you might take if you would like to ask questions about quantum gravity in the lab. And I think both of these approaches are represented in this conference. So one is asking, can we sort of build systems that are somehow massive and yet quantum mechanics at the same time plays a role? Can we do extraordinarily precise measurements in regimes where gravity and quantum mechanics are both relevant? So that's one approach to sort of directly probing gravity in our universe. And a complementary approach, which I'll get to in my talk today, is to ask, what if we start from the microscopics? We have more and more control these days of the quantum systems that we can build in the lab. Could we start by building an interacting quantum system, probing the correlations in that system, and asking whether something that looks like curved space or gravity emerges as a natural description of the correlations? So this is this approach of quantum simulation. I'd like to actually emphasize that both of these approaches really rely on sort of, broadly speaking, quantum engineering, so being able to build up well-controlled quantum systems in the lab, and much of the sort of hard experimental work that goes into this actually can have applications in both of these directions of precision measurement and simulation. And in particular, the toolbox I'll be talking about today, the experimental toolbox, is one where our quantum engineering, the sort of building blocks are laser-cooled atoms. I showed here a few pictures from labs around the world where it's even become possible to control and manipulate individual atoms, and at the same time have a high degree of scalability where hundreds of these atoms can be observed and detected and well controlled. So this is just broadly introducing kind of this cold atom toolbox as one that has applications. I'll talk about simulating sort of a toy model of quantum gravity, but one can also, there's broad interest here in everything from using these as precision measurement devices for extraordinarily precise clocks that can do tests of fundamental physics, simulations in a range of fields, including condensed matter, or even the building blocks of quantum computers. So for all of these applications, actually, one of the sort of key requirements is not only to have control and detection of the individual atoms at the single particle level, but also to have a high degree of control over the interactions amongst them, particularly for any sort of simulations of many-body physics or goals in computation. And here there's also a fairly well-established toolbox where typically one has local interactions. Say one might have atoms trapped in a lattice and they can interact if they're sitting on the same site, or even have some longer range interactions, van der Waals interactions that could extend over somewhat longer distances. But nevertheless, typically one limitation of kind of the standard cold atom toolbox is that interactions usually decay with distance. So atoms only kind of interact with their neighbors. And a focus in my lab has been actually trying to get beyond this limitation. And in order to be able to build up a wider range of quantum systems that could be of interest for, broadly speaking, a number of applications. So just to give sort of a flavor, why might you care to control the structure of the interactions? If one has, let's say, a collection of qubits, which are situated on a lattice, and one has nearest neighbor interactions, that's a very natural way to make a state known as a cluster state that is a resource for computation. If you had the same form of interaction, but instead every atom talks equally to every other, this is actually a natural way to make a state known as a squeezed state that is a resource for enhancing sensors and clocks. If one has some randomness in the structure of the interactions, this could be a way to realize the phenomenon of fast scrambling, which could be interesting for asking, can we build in the lab a toy model of a black hole, of a holographic black hole? And lastly, if one has sufficient programmability of the interactions, that can also be interesting for computations where one perhaps takes some computational problem that can be mapped to minimizing the energy of a specified interacting spin system, and one programs in the correct problem by controlling the graph of interactions. So this is kind of a broad motivation for having control of a quantum system where we can control the structure of interactions. And we've been working towards that in my lab by having a system where atoms can talk to each other with the aid of photons that can convey information not only between neighbors but also over longer distances. So the general platform I'll be talking about today is one where we have cold atoms and we situate them in an optical cavity that allows us to actually ultimately optically also control the graph of interactions in this quantum system. So that's kind of the general toolbox. I'm going to say a little bit more about how these photon-mediated interactions work and what we can do about them. So I'll continue in a moment to introduce the experimental toolbox and then say how we've applied that to realize a toy model of this notion of emergent geometry, of bulk geometry emerging as a description of the structure of correlations in a quantum system. So for the experts, this is something inspired by p-adic ADS-CFT. And then I'll proceed to also talk about ways of, in a more sort of engineered way, building up and directly detecting signatures of entanglement and the spatial structure of entanglement in this quantum system, and that will sort of lead into an outlook for future directions. So with that in mind, so I said that we will be using light to enable us to realize new kinds of non-local interactions between atoms. And so just to give you a sense of how does that work, in the simplest case, if I had just two atoms and I wanted to have a photon mediate a spin exchange interaction between them, what I can do is I can, so initially have one atom in state spin up, the other one in spin down, and what I need is some process where the up atom emits a photon, which gets absorbed by another atom, and in the process of absorbing and emitting and absorbing the photon, these atoms flip their spins. So that's a way that one can have a spin exchange interaction mediated by light. In our experiment that I'll talk about, we don't do this with just two atoms. We actually work with systems of many atoms. And I'll just mention this is a platform that already has a fairly well-established track record in the areas of, for example, using these photon-mediated interactions to generate useful entangled states. I've shown here some kind of sketches of entangled states that are described that feature some, they're described by sort of the collective spin of many atoms and the fluctuations, some Gaussian fluctuations around that. And by introducing interactions that generate entanglement, one can actually reduce those fluctuations in what's known as a squeezed state. And so this is one example of the types of kind of many particle states that have already been realized in these systems of atoms interacting with the aid of photons. One thing that you'll sort of notice if you look at this picture is these are systems where one is dealing with actually thousands of atoms in some entangled state, but it's still conceptually simple, right? I can draw a picture of it, and I can describe it in terms of collective magnetization and the fluctuations around that. So we're not yet sort of in this type of experiment accessing kind of the full many-body Hilbert space. There's work towards accessing kind of richer many-body physics, often inspired by themes of condensed matter. So for example, using photons in such a resonator to mimic phonons in a solid, studying topological states. And in this vein of sort of simulation, we would love to be able to kind of extend this toolbox to study, well, among other things, perhaps some toy models inspired by holographic duality and quantum gravity. And so in terms of extending the toolbox, let me show what actually the experimental setup in our lab looks like. So one of the ingredients that we've been adding is the ability to not only have photons mediate interactions, but have local control and detection. So in this setup, what we work with is typically an array of clouds of atoms that are trapped inside an optical resonator that will allow us to have these photon-mediated interactions. We work with, typically up to sort of 20 sites in this array, and each of those sites contains actually not a single atom, but an ensemble of thousands of atoms, which is convenient in that it enhances the strength of it gives us a collective enhancement in the strength of the atom-photon coupling. So each array site is going to be this cloud of atoms, and we'll be interested in controlling how those atom clouds talk to each other. So in order to have optical control over the interactions, our experiment actually, essentially, I showed sort of a cartoon picture of two-leveled atoms interacting, but in practice what we do is we have an interaction that involves absorbing a photon from a drive laser and emitting a photon into the cavity in order for one atom to flip its spin, so to change its internal state. And the second atom can then essentially reabsorb a photon from the cavity and re-emit into the drive field, and that will give rise to interactions in this system. So this gives us an optically controlled interaction that is on only if the light is on. And to add sort of one more wrinkle to the story, the atoms that we work with actually have a spin 1 ground state. And so typically the way that we kind of probe the system and probe the interactions is we often initialize the system with all atoms in the m equals 0 state of this spin 1 manifold. And in this case, when we turn on the light mediates a process of pair creation. So we start with, if you had just two atoms, you could convert two atoms in the 0 state into a superposition of +1 and -1. And so this you can already kind of see is a mechanism for potentially generating entanglement in the system. And actually that's this phenomenon of sort of pair creation in spin 1 atoms has actually been harnessed to generate entangled states in the past using direct collisional interactions. But the nice thing is our goal will be actually to realize similar interactions over millimeter scale distances in a way that is mediated by light. So the what does it look like when we try to do that? So here's an example of an experiment where we start with all of the atoms in the system initiated in the m equals 0 state of this spin 1 system. And we turn on the light for some period of time and later measure the populations in all 3 internal states of our atoms. So this is actually just showing 100 repetitions of the same experiment. And the 3 different columns here are showing populations in the 3 different internal states. And then each sort of pixel in the column is showing a particular site of the array. And one thing that we'll notice is that sort of if one looks at the different iterations of the experiment, there's actually large fluctuations in the populations of the 3 states, but the populations always appear to be correlated in that when there are more atoms in the -1 state, there are also more atoms in the +1 state. And that's kind of a signature that one would expect from this pair creation dynamics. Another thing you can see is that the correlations kind of extend across the entire millimeter scale array of atomic clouds. There's no sense of spatial locality here. So this is showing that in this extended array, any atom can talk equally to any other. But what we would like to do is actually, I said, have some control actually over the structure of the interactions. And in particular, in order to program, and we'd like to be able to somehow use light to program the structure, the graph of interactions in this system. And ideally, maybe you want arbitrary interaction graphs. We'll be a little bit more modest to start with and ask, can we at least build any translation invariant graph that we would like? And it turns out there's an elegant way to do this, where the first thing we need to do is to make the spatial position of each atomic cloud matter. And the way that we make the position matter is we apply a magnetic field gradient across the system. So by applying this magnetic field gradient, we realize a system where essentially there's an energy cost to creating these +1, -1 pairs unless the 2 atoms involved are sitting on the same side of the array. And as a result, if we measure correlations between, let's say, the population in the +1 state on site I and the population in the -1 state on site J, we find that the correlations are strong on the diagonal of this plot. So the on-site correlation is strong between the + and -1 population, and is sort of negligible as soon as one goes off-site, which is to say the interactions are occurring only locally. So we had completely global interactions. We can realize local interactions. And now what we would love to do is controllably turn on interactions at a distance of our choice. And that's also something we can do. It turns out we can do this by essentially adding a second frequency component to the drive field that we use to turn on interactions. So now one can have processes where an atom absorbs a photon of one frequency, emits a photon of a different frequency, and so that allows the light field to bridge the energy cost of creating these +1, -1 pairs at a particular distance. And so that shows up in this particular case. We chose the modulation frequency so as to generate interactions at a distance of 10 sites. So every site talks to the site that's 10 away in the array, and that shows up in these off-diagonal correlations. Now and literally what we're doing here is we're just modulating the intensity of the laser field that is driving the system. And by changing the frequency with which we modulate, we can change the distance at which the interactions are on, and hence at which we observe correlations. So this plot here is showing the x-axis is each row is showing correlation strength as a function of distance in the array. Vertically, we're varying the modulation frequency, and we see that the distance where the correlations are strong tracks the modulation frequency. And if you zoom in, you can see that you can really control this in discrete steps of 9 sites or 10 sites or 11 sites in terms of where the interactions are on. So this is a nice start, and the really great thing about this is actually we don't have to just modulate sinusoidally. We actually can easily change the modulation waveform of the laser field in order to generate richer graphs of interaction. And to give sort of a framework for thinking about that, I actually kind of like to give you kind of 2 complementary pictures for how we think about this. So one is that actually, I said before, kind of the spectrum of the drive field, the frequency components that are present, will dictate the structure of interactions that we have as a function of distance. So each frequency difference in my spectrum corresponds to some distance at which I can generate these correlated pairs. Or you can kind of Fourier transform that picture and say, well, in momentum space, that means that if I take the Fourier transform of this spectrum, that gives me the drive waveform. And that drive waveform actually sets the dispersion relation for spin excitations in the system. So I can either say I have a Hamiltonian where these couplings are set by the frequency spectrum in real space. Here the big F represents the collective magnetization on a given site. Or equivalently, I can sort of say that the waveform as a function of time gives me the energy of different spin waves in the system. And it turns out that for our particular system, this pair creation, there's essentially an instability to creating these correlated pairs, and the instability is strongest at the minima of the dispersion relation, which are these maxima of the modulation waveform. So then if one looks at the data, it also kind of matches what you would expect from both the real and momentum space pictures. So in momentum space, we can think of essentially having some peaks that grow at particular momenta corresponding to the minima of the dispersion relation, and that shows up if one looks at the dynamics in time, as these peaks sort of grow and get narrower, one sees correlations spreading. In this particular case, I've turned on interactions at a distance of 3 sites, and as a function of time, you can see correlations spreading from 3 to 6 to 9 sites and so on. So one can also kind of look at the dynamics in the system, and it behaves in a sensible way. So now, one actually nice trick that we thought of by thinking actually in this momentum space picture is we're dealing with a finite size system. And so this dispersion relation is actually only defined at discrete points in momentum space. So if I take that seriously, that means maybe I shouldn't be having this smooth sinusoidal modulation. Maybe what I really should be doing is pulsing on the drive field at discrete times. And it turns out if you do that, you generate precisely the dispersion relation for the finite size system with periodic boundary conditions. And so that means this actually is a nice trick where just by deciding do we smoothly modulate or do we pulse the modulation waveform, we can go from, for example, in the case where the smooth modulation would just give a nearest neighbor chain with open boundary conditions, if we add this additional pulsing, it essentially connects the ends of the chain to form a ring. And this is a very general trick for taking whatever interaction graph we'd like to make and adding periodic boundary conditions. So, I can tell you that that's what, that's how to read this correlation plot. But more generally, what can be useful is actually asking, can we go from the measured spin correlations and in kind of a black box way reconstruct what is the interaction graph that we made? So we can do that for this example where we think what we should have is a ring, so nearest neighbor interactions and periodic boundary conditions. So we drive the system with an appropriate waveform, we measure some correlations, and now we can ask, what is the kind of best geometrical representation for the interaction graph that we've generated? And so what we can do is say essentially from these measured correlations, let's assume some ansatz under which the correlations decay as a function of distance. For our system, it turns out to be natural to assume a Gaussian decay. And the idea is that we'd like the correlations to decay as a function of distance in some effective geometry, which we'd like to identify. So we can ask, what is the best fit embedding of the array sites in 3 dimensions, let's say, such that correlations decay as a function of distance between some effective coordinates of the sites. And so we sort of do a best fit and find that in this particular case, indeed, these effective coordinates form a ring. And furthermore, actually, by using this correlation matrix, specifically the inverse correlation matrix, one can extract essentially what was the strength of the couplings. That's shown here in red. Or more generally, what I should say is actually in this system of n sites, there are kind of order n squared possible bonds that you could draw. And all of them are drawn, but the opacity and the color of the bond is based on the measured correlations. And what pops out is this ring indicating that we've successfully engineered the correct interaction graph. So this is a nice way of also kind of verifying the geometries that we generate. And now one can, apply that to other systems. Here's just to give a few other examples. If we started with just open boundary conditions and third neighbor interactions, we measure some correlations that I showed before. And this best fit geometry that pops out are 3D coupled chains. And that actually makes sense because I could have drawn the graph like this. But we can also be fancier and let's say have this ring, nearest neighbor interactions, periodic boundary conditions. Let's also add some interactions across the ring. So we'll add in these ninth neighbor interactions. And we can even control the sign of the interaction via the phase of the modulation waveform. So here we made the neighboring interactions ferromagnetic. These interactions across the ring are anti-ferromagnetic. We measure some correlations. And now you can look at this and see whether you can figure out what geometry will be the best description of this coupling graph. And what one finds actually in this case, this is actually a Möbius strip, right? So the ring is the single edge of the strip, and these sort of crossbars here across the wheel are these ladder legs in the Möbius strip. So I think this nicely kind of illustrates the platform where we have flexible control over the graph of interactions that we can program in with light. Here's kind of a gallery of a few of the other coupling graphs that we've realized in this way. So now we would like to use this as a tool for a number of directions, but the one that I will talk about is asking, can we use this control of the interaction graph to build some kind of a toy model of holographic duality? So maybe before I do that, I'll just pause and ask, are there questions about kind of this experimental toolbox? I don't know if there's a way for people to ask questions, but I'd love to have questions along the way. I think I see a hand raised.
Thank you. I was wondering, can you consider dissipation effects when you simulate your system, your interaction with through photons? Maybe you want to connect some atom that's very far, and when the atom decays, that photon will go out of the system. Can you consider that kind of interaction?
Yeah, so in general, I would say with these photon-mediated interactions, dissipation is never completely negligible. In the regime we're working in, we try very hard to operate in a regime where what we observe is actually kind of well described by neglecting the dissipation. But in general, there's always the possibility that rather than the photon being scattered between two atoms, the photon leaves the cavity and you have sort of one spin flip instead of these pairwise spin flips. And so I mentioned that we kind of work with atomic ensembles, and that's actually so that we can kind of enhance the interaction to dissipation ratio in our system. And that's also sort of the reason for having kind of a good optical resonator, is that one can maximize kind of the strength of coherent interactions relative to dissipation. But there are actually ways of tuning to a more dissipative regime if that is of interest. So one can actually, by changing essentially how close, so there's this Raman process where you flip a spin and put a photon into the cavity, and that's a virtual process. We don't make it resonant, but actually if one tunes that process closer to resonant, then collective dissipation will become more important compared to the coherent interactions. And so that could be an interesting knob to explore. So far we try to minimize the dissipation, but it could be interesting to explore.
Okay, thanks.
Great question. Are there other questions? If not, I'll proceed to say a little bit about what you can do with this toolbox. And so in particular, for this audience, I want to focus on an experiment that was really inspired by asking, can one explore this notion of geometry emerging from quantum correlations in some toy model in the lab? And so this toy model was really inspired by conversations with Steve Gubser, who was thinking deeply about this question of kind of what is the mathematics behind the reality that we experience as smooth space-time, but which in all likelihood is discrete at a fundamental level. And Steve had formulated a version of the ADS-CFT correspondence known as p-adic ADS-CFT, where essentially the role of the holographic bulk geometry is played by a tree graph, which you can think of as a kind of a discretized version of a hyperbolic space. Right? If I have n sites at the base of the tree, I have only log n sites in the depth of the tree. And so if I think about it sort of with periodic boundary conditions here, the circumference is exponentially larger than the diameter. And so this can be thought of as kind of a discretized version of a hyperbolic space. And so in this p-adic ADS-CFT correspondence, the idea is that the quantum field theory lives on the boundary, and the bulk geometry is kind of really embodied by this tree graph. So we kind of asked ourselves, is there a model one could build in the lab where the physical system can be thought of as somehow living on the leaves of a tree graph? So here's the toy model that we came up with initially just on paper in collaboration with Steve. Where the basic, so the model is essentially one has sites that interact if the distance between a pair of sites is a power of 2. And there's a tuning parameter, which is sort of a power law exponent, that says for at those power of 2 distances, do interactions shrink with distance or do they grow with distance? So if S is negative, interactions shrink with distance. And in that case, the system is not too different from a nearest neighbor spin chain. We can make it, let's say, with periodic boundary conditions. But if S is greater than 0, then interactions grow with distance. So physically, the interactions between physical furthest neighbors are actually the strongest ones in this model. And the conjecture was that this is a system that would be well described by thinking of the sites as living at the leaves of a tree graph. That might not be obvious if I plot the coupling graph in the way I've shown here. It becomes maybe a little bit more believable if you rearrange the sites in a certain way. Maybe you can start to see some kind of a hierarchical structure to the couplings here. But what we'll actually do is we can build this model in the lab, and we can ask how do the correlations that result from these interactions behave, and is this tree graph the right way to think about them? So we essentially build this model with either S less than 0 or S greater than 0, what we think should be kind of the linear and the tree-like regimes. And we measure correlations as before, spin correlations among the sites. And now if you take this exponent greater than 0, this weird system where interactions are strongest for large powers of 2, and you plot correlations as a function of sort of the physical position in the array, you'll see kind of a non-monotonic behavior. Not surprisingly, peaks are kind of at power of 2 distances. And one way to check whether we have realized something like this tree-like bulk geometry is to actually apply a map that should take us from position in the physical system to position on the tree. And it turns out that map, what you need to do, you can sort of think of this tree as being formed by writing down the site number in the array in binary, and depending whether each bit is 0 or 1, you go either left or right in the tree, starting from the least significant bit. So all the even sites are on the left, all the odd sites are on the right, and so forth. And so now, so we can ask, well, what does this correlation plot look like if we apply this map of reversing the bit order? This is known as the monomap. If you apply this and just replot the same correlations in this rearranged order, you'll start to see a bit more structure in the plot, right? So now in this rearranged order, it actually kind of looks like there's some hierarchical block structure emerging. You can maybe kind of see a block of 8 here. You can certainly see blocks of 4, blocks of 2. And that kind of matches this hierarchy associated with the tree graph. And in fact, one can also even take the correct notion of distance on the tree, which is related to how many levels of the tree you need to go up to connect 2 sites. And if one plots correlations versus this two-adic distance, they in fact smoothly decay as a function of this distance in the tree. And so that's a first indication that yes, in fact, thinking of the sites of our array as living on a tree graph is actually a fairly natural description. But we can take this one step further and ask, is there a way that we can kind of really reconstruct this tree-like bulk geometry directly from the data? And earlier I showed you some examples where we are able to reconstruct, let's say a Möbius strip from our experimental data. But that's a little bit different because there each site in the thing we reconstruct is physically a site in our array. For this tree graph, the notion is that sort of the interior vertices of the tree aren't physical, only the leaves are physical. So how might you reconstruct that? Well, we'll start by doing the same thing we did before. So we can essentially ask, based on the measured spin correlations, can we find some coordinates of the sites, let's say in 2 dimensions, such that correlations decay as a function of distance. And so the first thing that we get, these black circles here show kind of these best fit coordinates obtained from the spin correlations. And now we're going to go one step further and ask which pairs of these sites are most strongly correlated. And in particular, what we will do, we'll just measure spin correlations in the X basis and look for pairs of sites that are strongly correlated, and we'll connect them. And actually, if you built the model that's sort of where nearest neighbor interactions dominate, then you immediately sort of connect each site to its neighbor and form this ring. But if you build the model where furthest neighbor interactions dominate, the first thing is that everything gets connected in pairs. And now if you sort of treat each of those pairs as a larger site and repeat the process of asking where are the correlations strongest until everything is connected, what pops out is in fact precisely the tree graph. So we were quite happy with this, that sort of in essentially a black box way, just from the measured spin correlations in the system, we can reconstruct this bulk geometry of the tree graph that's, again, these vertices aren't physical, but aren't physical sites in our array, but they're capturing something about the structure of correlations that arise from the interacting spin system that we've built in the lab. Okay, and so you have these actually 2 really radically different geometries, the ring and the tree, that come about just by tuning this sort of single parameter that's saying do interactions shrink with distance or grow with distance. One other fun thing you can do is ask actually what happens if I place myself right in between. So we said if this S is -1, then we see this kind of ring appear. If S is +1, we see the tree. But more generally, you can actually also ask what happens if I sort of vary this parameter S in between. And we can specifically also ask how strong are kind of correlations between different halves of the system. So actually in this plot, what we've done is we've said for different values of this tuning exponent S, how strong are the correlations between 2 halves of the system if we cut according to either the physical geometry or according to this tree-like geometry. And so if S is +1, then cutting according to the tree is the right thing to do to minimize the correlations between the 2 halves. That's the green here. If S is less than 0, so that we have roughly nearest neighbor interactions dominating, then you should cut according to the physical geometry in order to minimize the correlation between the 2 halves. But actually, if S is equal to 0, there's no way you can cut the system so that the 2 halves are weakly correlated. So neither the cut according to the physical geometry nor the cut according to the tree reduces these correlations. And in fact, if you look at all possible bipartitions of the system, that's the purple here, one sees that there's kind of a peak where the correlations are strongest if this tuning exponent is set to 0. And this is actually an interesting point where in some sense you could say every site in the array is close to all others. And we have, this actually looks like a very promising regime for studying in future experiments fast scrambling because of the sort of high degree of connectivity in this interaction graph. So that's a future direction. One other thing that I sort of want to point out about this plot, so here what we're doing, I say we measure correlations, and really it's sort of the simplest experimental measurement you could do. It's just measure the spins in the X basis, measure the correlations between the sites. But actually the data look not too different, at least qualitatively, from something we had put into a theory paper that was kind of proposing this experiment a couple of years back, where instead of this sort of simple experimental measurement in the theory paper, we had plotted entanglement entropy. And in a similar way there, this is for a spin chain with a single spin half per site, but in a similar way there, one expects the entanglement entropy to peak when one sets the tuning parameter to 0, such that sort of every site is close to every other. So, one question that this kind of raises for me, on the one hand, it's nice that a simpler experimental observable gives at least qualitatively similar behavior. But another question is, so far we've just been kind of measuring correlations in a single basis. Can we take this a step further and start to actually detect entanglement in our experiment? So, lest you be disappointed, I won't be talking about measuring entanglement in the tree graph. But I will say a little bit about kind of recent work that we're doing on being able to kind of detect entanglement and probe its spatial structure in some simpler models in our system. Maybe I'll just pause again though and ask whether there are immediate questions before I go on. Yes. Mm-hmm.
Sorry, just to make sure. So the state you realized on this graph state is the ground state, or is it the kind of highly?
Yeah, this is a very good question. So what we do in the experiment is we just initiate the system, in a simple state, the state where all atoms are in the m equals 0 spin state, and we turn on interactions suddenly. And so naively, it's sort of, there's no reason to expect anything like a ground state. It's a dynamical experiment. One thing, though, that is kind of worth pointing out, and maybe I'll just take a step back here. I kind of mentioned that in our system, let me look here. Essentially, the dynamics are actually such that essentially there's an instability to forming these correlated pairs at momenta that correspond to the minimum of the dispersion relation. And so actually there is a sense in which the states that we generate look like low temperature states of a classical XY model on this graph, even though it's actually a dynamical experiment. And so, when I showed, for example, let's see, some of these pictures where we infer these bonds that are couplings from the spin correlations, one actually sees the spin correlations in the system kind of match what you would expect for a low temperature state of an XY model on this graph.
Yeah,
but it is a dynamical experiment of a classical XY model, but it's a dynamical experiment.
I see. So in some sense, can we regard that the state is a kind of initial state of quantum quench where you suddenly change the Hamiltonian, and
yes.
So it's highly exciting. So for us, that so it's more suitable to study the holographic duality because this is somehow related to black hole micro, one of these black hole micro states. Do you have any perspective on this?
So can you repeat? So what is related to black hole microstates?
Yeah. So for me, it seems like that the state you prepared is a kind of state prepared in quantum quench protocol.
Yes, that's right.
So this So through this holographic duality, so this such an initial state of the quantum quench can be regarded as one of the black hole microstates.
Okay.
So in that sense, so the state you prepared is more suitable to study, chaotic dynamics of black holes or something like that. For me, I'm not familiar with these experimental, the setups, so I'm not sure, but so as long as I'm listening what you have been saying, this is much more related to black hole microstates.
This is I will take that as a comment. I'm not sure that I would love to learn more about that connection. I haven't thought about it in that way.
Sure. Thanks.
But I would love to learn more about that. And again, it's certainly true that we're not preparing a ground state or a thermal state. We are doing a quench. So, Mm-hmm. Great.
Can I ask a question related to point? So you showed this nice graph of entanglement. And can we think that they are area law state or volume law state? Usually, if we think three tensor network like state, it looks like area law state.
Yeah, so this is actually a good question. So sorry, now I'm just trying to get back to the plot you're referring to. So in the theory, we looked here at, essentially entanglement entropy for different cuts, either sort of cutting according to the tree or cutting according to the physical geometry. And I have to, we probably should have looked at how it scales, and I have to admit that we did not do that, and it's a very good question. I think the main sort of point that we were looking at here is that essentially, when you talk about kind of, is it area law, one has to actually think first about kind of where am I, how am I doing my cut? So because there are sort of two ways of thinking about the system, either the sites are arranged in their physical order, or I arrange them in this monomapped order. And in order to see kind of the lowest possible entanglement when I cut the system in half, if I'm in this tree-like regime, it's important that I first rearrange the sites according to this map, right? So I have the even sites on the left and the odd sites on the right, and that will give me the smallest entanglement. And if I were to sort of cut in the wrong way, it might look larger. But now, is it scaling? So, and if it is in fact an area law, I guess that would say, I'm just thinking what that actually means in this case. I think for the linear chain, it's pretty clear that if I do this half cut and it's area law entanglement, then that basically means the entanglement is essentially constant, right? Because I'm just cutting one bond.
Yes.
And for the tree, I think that's still the same if I cut it in half.
Yeah, also looks like area law if we cut that.
Yeah, and so I think I would conjecture that it's an area law as long as you cut it the right way, but we didn't actually look at the scaling directly. So yeah, so that's a good question.
Yeah, because if this is related to black hole, it's like volume law. So we are very quite keen to this difference.
Oh yeah, so sorry. And so the claim would be that if there is a place that's acting like a black hole, it would be this this special s equals 0 point, where that's where there's this peak in the entanglement, right?
Maybe that point might be volume law.
Yeah, and so now, so this is a good question. How does that scale, and is that a volume law? That's a very good question. And I guess one could ask it about the system after a quench, which is what we're looking at here. You could, of course, also ask it about ground states or thermal states in the model, and I think that would be nice to explore on the theoretical side.
Thank you very much. That's very cool.
Yeah.
I have a yes. Can I ask?
Yes.
So I have a quick question. What is P in the p-adic ADS-CFT?
Oh,
is that the number of legs or?
Yeah, exactly. When one makes this, so I've been focusing on 2-adic, which means it's this binary tree, but you could also separate into 3 or so forth.
Great. Then my question is, for example, can you implement like 3-adic ADS-CFT or something? Because if it's 3, I think you need maybe many partite, like multi-partite interaction. Can you implement it?
Oh, so
in the case of 2-adic, I think it's just like I minus j. Or something.
I actually don't think that we need multi-partite interaction. I think it would be sufficient to use powers of 3 instead of powers of 2 in the way that we construct the coupling graph.
Okay.
It's so, and if that's
so
true,
what is the interaction in this graph? I thought
if I go back to the Hamiltonian.
Yeah.
So right now, sort of interactions exist between sites that are separated by a power of 2 distance. And I believe if it were, if I wanted to make it 3-adic, I should make these power of 3 distances, but it could still be a 2-body interaction.
But then it's just a matter of kind of distance, is correct?
Yeah, exactly. Right. So it would still be a 2-body interactions, but it would be a different coupling graph. And so I would say the reason that we, haven't done that, well, first of all, I'm not quite sure whether there's something new to be learned. If it were 3-adic, that would be interesting to know. But also, it just requires more sites, and so there's room, I think, to increase the number of sites in our system. So far, we worked with 16. We're thinking about going to something like 64, but I think more than kind of anyway, it's easier to have more levels of the tree if it's 2-adic than if it's 3-adic. So, yeah.
Okay. Yeah. Thank you very much.
Yep. Okay, so I think I'll keep going perhaps, and then because there's a few more slides, and then take more questions at the end. Is that okay? The moderators. Oh, is there another question?
Just
yeah,
quick
okay.
question. It's one-dimensional edge, right? And two-dimensional ball in space,
yes.
right?
Yes.
I'm wondering how do these graphs that you've shown behave in terms of space-time? I mean, the dynamics of the graph. How these look like?
So how do they behave in terms of space-time?
Right.
I'm actually not quite sure I understand the question. So, in some sense, yeah.
Yeah. How does it behave in time?
So I think the time dimension. We don't really have control over it in the way we have control over the spatial dimension. So I think one thing is that in this sort of p-adic ADS CFT, like actually on the theoretical side, my understanding is that sort of knowing how to make the time dimension p-adic is actually a sort of a challenge. But experimentally, in terms of just this model, we can So I mean, we're essentially measuring dynamics. We're doing a quench.
It's just decay.
But I'm not quite sure what. I guess I need maybe a sharper question about.
Oh, thank you.
Yeah. I think perhaps if there's a specific question about how it evolves in time, I could maybe. So I mean, we see correlations. I guess what I could say is we see correlations spread on the graph that we've engineered in some sense. And in some sense, I do think that in this tree-like geometry, right, the tree graph gives some way of thinking about how correlations will spread as a function of time. But I'm not sure whether that answers your question. And sort of how quickly they'll spread to different places is sort of governed by how far apart things are in the tree graph. Okay, so maybe I'll leave it at that for now, and we can, if there's time, come back if I didn't answer it. So with that, I think I want to just say, do I have time to say a few words about kind of engineering and probing entanglement in this system? Nobody is objecting, so I will do that. Right, so it would be wonderful to be able to sort of look not just at this kind of simple measure of spin correlations, but say a little bit more about entanglement. Lest you be disappointed, we will not be measuring entanglement entropy. But one way that we can actually say something about entanglement in our system is to look at actually squeezing of quantum fluctuations. So this is kind of drawing inspiration from the field of quantum sensing and metrology. And in particular, this kind of I mentioned earlier, these pair creation dynamics seem like a mechanism for generating entanglement. And in particular, one way that one can see that is actually by looking at squeezing of quantum fluctuations in this sort of on kind of a generalized Bloch sphere, where in particular the axes of interest involve essentially collective spin and quadrupole moments of our atomic ensembles. So in the simplest case, if we have, I'll show some data where we're dealing with just 4 atomic ensembles. And the first thing you can ask about is if I don't do any programming of the interactions, I just have the simplest all-to-all interactions, this essentially behaves like a single large ensemble. And what one expects from the interactions that we engineer is that one essentially starts with a state that's a sort of isotropic Gaussian, has Gaussian fluctuations that get squeezed as a function of time in this when we turn on the interactions on some generalized Bloch sphere. So this is something that we can measure in the experiment. Essentially, we can turn on the light and at some later time measure the fluctuations in the collective magnetization after doing some rotation on this sphere. And as a function of rotation angle, we'll see that in some direction the fluctuations dip below the standard quantum limit. So this line is essentially the smallest that the fluctuations could be if we just had n uncorrelated atoms. And so this is a way of demonstrating that there is entanglement in the sense that this n-atom system cannot be represented in a separable form. But you'd like to also go one step further and say, can we access something about the spatial structure of entanglement in the system? And so, for example, you could ask, if I'm looking at the left half and the right half, can I establish whether these two spatial modes are entangled with each other? And in order to do that, we can ask essentially, how much information can I gain about the system A from measurements on system B? And in particular, can I learn something about two different non-commuting observables? So the idea is, if I had a separable state of these two subsystems, for now, just for simplicity, let's just think of these as oscillators. So each one has a phase space x and p. And if I have, if the system is separable, then you can write down a Heisenberg uncertainty relation of this form. So for a separable state, the uncertainty in the sum of the x's for these two subsystems and the difference of the p's, that product of the uncertainties is larger than h bar. So that's true if the subsystems are unentangled, but in general, there's actually no Heisenberg uncertainty bound on knowing both of these quantities because xa plus xb commutes with pa minus pb. And so in particular, if one has an entangled state, then one can violate the condition that this uncertainty product is larger than h bar and make it arbitrarily small. So that's something we can look at in our system. This was termed the quantum mechanics-free subsystem in the quantum metrology context. In our system, we can look again at this measurement where I said, if I look at kind of the symmetric mode, where I look at xa plus xb and pa plus pb, I showed you before this measurement of the fluctuations kind of as a function of angle and phase space. And if I additionally, though, also now look at the anti-symmetric mode, where I look at xa minus xb and pa minus pb, I can get a similar curve, which essentially looks flat, and that's because the cavity actually doesn't couple to this anti-symmetric mode, and so the quantum fluctuations are not squeezed in this mode. But from basically by looking at essentially one quadrature of the symmetric mode and the orthogonal quadrature of the anti-symmetric mode, we can construct essentially an entanglement witness based on the products of variances. And if this is less than 1, then the two subsystems are entangled, and that's true in this experiment. So now we're starting to get at the spatial structure of entanglement. We can verify entanglement between the left and right subsystems. And one other kind of signature of the fact that these subsystems are entangled is that if you were to look at just a single one alone and ask, is A internally squeezed or is B internally squeezed, you actually see the squeezing is degraded. So these curves aren't really dipping down below the standard quantum limit, and that's to be expected because I've cut the system in half and just looked at one half alone, and it's now in a mixed state. It turns out actually if you want to have some control over the structure of the entanglement such that instead of having entanglement between the two ensembles, we just have entanglement within mode A and within mode B, we can do a more sophisticated experimental sequence where we apply this global interaction that squeezes, then do a local pi rotation on one subsystem, and then apply the global squeezing again. And it turns out this intermediate step here actually disentangles the two subsystems from each other and produces stronger squeezing within the individual modes. So this is kind of getting at a general kind of vision of asking, can one start to have programmable entanglement in this quantum system? So we can make global entanglement. We could make arrays of independent squeeze states by this disentangling trick. And most recently, though, we've also been asking, can you start to make, for example, cluster states where there's some structure of entanglement that I can represent by a graph, where the bonds in the graph essentially mean that X on a given site is correlated with P on the site to which it is connected. So it turns out actually there's a very nice way to go from any graph that you specify. I can sort of specify it by what's known as the adjacency matrix. That's just the matrix representation of this graph. And if I want a prescription for making this state, what I can do is I can actually take the, diagonalize the matrix. The eigenvectors are going to specify a set of collective modes that I should squeeze. And the orientations of the squeezed quadrature are just given by the eigenvalues of the matrix. So this is nice because essentially, like in the simplest case, I showed the example here of just, this is the minimal instance of a cluster state. It's all equivalently could be thought of as an EPR state, where I just have two spatial modes, and what I should do is essentially squeeze the sum mode, the symmetric and the antisymmetric modes in orthogonal quadratures. That's a thing we can do. We apply global interactions, a local rotation that converts the symmetric to the antisymmetric mode, a phase space rotation and another squeezing operation, and the net effect is to give us something where the symmetric mode is squeezed in one quadrature, the antisymmetric mode is squeezed in the orthogonal quadrature. And here, actually, for this state, so this is really kind of EPR type entanglement between the two modes, and that entanglement witness is now sort of smaller because we've maximized entanglement between the subsystems as opposed to within the subsystems. And so this general approach of kind of specifying the graph of correlations that we'd like, and then figuring out which collective modes to squeeze, and implementing that this generalizes. Most recently, we've used this to make a 4-mode cluster state, square cluster state that's represented by this graph. And I think, in some sense, to me, this is kind of a nice demonstration both of the ability to start to control the spatial structure of entanglement, but also to detect the spatial structure of entanglement in the experiment. And we would love to actually kind of apply that then also to quantum simulations where perhaps one doesn't know a priori the structure of entanglement and wants to learn something about it. So just to summarize, I've shown you an experiment where we have programmable interactions between atom clouds in an array in our cavity. I talked about the emergence of a tree-like bulk geometry that we can sort of directly reconstruct from the measured spin correlations in our system. And we would love to get sort of really closer to the heart of connecting geometry with actual measures of entanglement. And as a step in that direction, we've been first kind of engineering specific entangled states and showing that we can characterize them in the lab. So in terms of kind of prospects, I would love to sort of ask, can we have some interesting models where we expect perhaps it's this tree-like emergent geometry or some other emergent geometry, but can one start to actually reconstruct that really from measures of entanglement in the experiment? And for us, entanglement entropy isn't the most natural one to access, but I've been happy to see some papers like this one, Distance Between Quantum States and Gauge Gravity Duality, that look at sort of other kind of measures such as fidelity susceptibility, sort of sensitivity to perturbations that are kind of more natural potentially to probe in experiments, and exploring how those are connected to geometry, to bulk geometry. So that could be an interesting future direction to explore in experiments. We'd also like to kind of explore perhaps variations on this sort of tree that I can think of as a discretized version of anti-de Sitter space. One idea coming from Matt Heidemann, who's a postdoc at Princeton, is to sort of add a black hole horizon to this geometry that we've realized, and that's something we're interested to explore. I also mentioned that there's sort of a special point where we expect this model to be a fast scrambler, and so looking at kind of the dynamics as one tunes to that special point and also away from it, or perhaps also exploring other types of interaction graphs, like more random forms of couplings, and asking, can one see fast scrambling in the system is another future direction. And lastly, I should just emphasize, I showed a lot of data where what we're looking at are sort of the average magnetization and also the fluctuations. And so far what we're doing, because we're working with kind of large atomic ensembles on each array site, we can so far kind of analyze the dynamics using semi-classical methods. We would love to get to a regime where you really can't calculate things and you have to do the experiment, and that involves going to sort of stronger atom-photon coupling so that one could have a single spin per site, and that's a direction that is sort of one for future technical upgrades to the experiment. So with that, I just want to thank the team who have made these experiments happen. In particular, these three are the graduate students and postdoc who have worked on the experiments I talked about today. And I also want to particularly mention, I mentioned earlier, Steve Gubser as the inspiration behind exploring this tree-like geometry together with my student Greg Benson, who worked on some of the early theory motivating that experiment. And with that, I'll take any questions, if there's still time. So.
Thank you for very interesting talk. Now the session is open for question and comment. Is there any question?
Excuse me, in the previous slide, for fast scramblers, do you need some other schemes of controlling the interactions than, say, I minus j equals something? So you had, I mean, distance is like paths of 2 for the tree-like geometry. But for the geometry on the slide, the cube-like geometry, you need some different control.
Okay, yeah, so this particular picture I've drawn is actually a representation of the model where interactions are on at power of 2 distances, and they're equal for all powers of 2. So this is kind of this special point where the interactions neither shrink nor grow with the physical distance.
Okay.
And so that, in some sense, you can think of it, the kind of original concept that led us to start thinking about this model is that if you sort of ask what is the distance in the graph, these sort of power of 2 couplings allow you to get from one site to any other in kind of log n hops. And so that's kind of, and so that was actually the original kind of motivation behind thinking about these types of models, is that the characteristic time scale to get kind of from one point to any other in the graph should scale as log n and not as n. In kind of to the extent that we've been able to look at this theoretically, which means either for small system sizes in the sort of spin half model or in the semi-classical regime at larger system size, it does sort of exhibit key features you'd expect from a fast scrambler in terms of this characteristic logarithmic time scale. And so I mean fast in terms of the characteristic time scale being log n. There's a separate question about sort of low temperature behavior, which is not something we've looked at. So in this case, I mean fast scrambling in the sense of this logarithmic time scale. Yeah, and so that would be in the particular model, just tuned to that special point that I called s equals 0. And it's interesting because it's not a random graph, and it's a sparse model, right? So it's very different from, let's say, something like SYK.
Yes.
I think there's another direction where one could say, can one introduce more randomness in the couplings and explore things that are more SYK-like, let's say.
Another question, thank you. And another question is, so can you introduce 3-point or 4-point interactions like in SYK?
Yeah, that is definitely not easy in this setup. And generally my intuition is that if I were to try to engineer some higher body interaction, it will be hard to make it coherent. So you could imagine some multi-photon process that would give you a 4-body interaction. But my sense is that kind of it won't scale well in terms of the interaction strength compared to dissipation rates. I think there are other cold atom platforms where there could be possibilities. So for example, there are proposals for realizing 4-body interactions mediated by some ancilla atom, which could be done, let's say, potentially with interactions among Rydberg atoms, although there getting the non-locality is harder.
Okay.
And so perhaps one needs to kind of combine the best of a couple of different platforms in order to get that. I think there's a path, but it won't happen tomorrow. So, yeah.
I see. Thank you very much.
Yeah.
Any other question? Oh, yeah.
Thank you for the great talk. I have a question about the scalability of your system. it seems, your current system is like 16 atoms or something.
Yeah.
And you mentioned you tried like 64 atoms, right? And in principle, how many qubits, I mean, how many atoms can you deal with? Or is there any limiting factor?
Yeah, so this is a great question. So right now, actually, I said we would actually, for this black hole horizon story, we would like to make our tree deeper. And so it turns out to get to 64, the main limitation is laser power, and we're about to install a new laser, and we think we can get to something like, 64 in that system. But more sort of thinking longer term, right now we're working with kind of these clouds of atoms, and at some point it would be interesting to push towards sort of stronger single atom, single photon coupling, and having, in that case, actually the array sites, if one had just a single atom per site, could also be more closely spaced. And roughly speaking, there's a millimeter long region, and you need only kind of micron scale spacing between the atoms. So I think having a few hundred is not unreasonable in the longer term.
And if you want to have like 1,000 or something, if you want to go beyond 100, then you need more power or something, or is it impossible?
So I think it essentially comes down to, there's a certain spatial resolution one can get for trapping and imaging the atoms.
Oh, okay.
And using these photons to mediate the interactions, essentially there's some strongly coupled region where the light is tightly focused, which in our experiment is about 1 millimeter long. And if you try to make it longer, then the atom-like coupling will go down. There's a direction, actually, I showed a picture here of a very different type of a cavity. So right now we work with optical photons. We're actually building an experiment where instead we will have a superconducting millimeter wave cavity. So these would be photons around 75 gigahertz that couple to transitions between Rydberg states. And this is actually interesting because you could fit a lot, the strongly coupled region is kind of centimeters long, and the atom-photon coupling is substantially stronger. It's a very different technology, so this is still at an early stage, but I think long-term this could be interesting for really packing in kind of many atoms with single atom, deep in the single atom strong coupling regime, and so I think eventually, but frankly, I would say if you have 100 atoms, that's already, and you really are in the strongly interacting regime, that's already hard to simulate classically.
Sure,
so, right, yeah.
Okay, thank you very much.
Yep, yeah.
Any other question? Okay, then if not, then let's speak again.